So we're the weird people who are trying to use ShipConstructor to build houses. I'm probably the oldest guy in the room, I think, because I spent more than 30 years doing large-scale innovation projects for mostly companies like Volvo, IKEA, and Microsoft. So I'm just new to this construction industry. I work with a consortium that's funded by the Swedish government with some players, the public housing authorities in Sweden, some of the major construction firms. So I think the consortium turns over 9 billion euros per year, which is in Sweden pretty big. And we have the ambition of really redesigning the whole way houses are built, because it's the least digitized industry on the planet. It's also the industry that has the lowest productivity growth since basically the Second World War. So, and the costs, the last 20 years, residential building cost has risen 8 times faster than the consumer price index. And this is not just Sweden, it's kind of an international phenomenon. So when we started looking at that, it's obvious for me, it's no point talking to the construction firms, because if they had any ideas, they would have done it, years ago. So we started looking for industries where we could steal ideas. And a lot of people look at automotive, aerospace, but it's a fundamentally different thing when you build factories that's targeted for a certain platform. So we ended up with thinking maybe ships, You guys do one-off large complex projects. So we started benchmarking, and especially cruise ships, they are like small cities. So we started benchmarking how long time it takes and how much it costs to build a cruise ship, Harmony of the Seas, for instance. And we compared to if I would build all those things, all the things that are on that ship on land, and we discovered it would cost many times more on land with the construction industry than a ship. And a ship obviously have a hull, some engines, and a lot of stuff that you don't need in a city. So that's why we ended up with, how are you guys doing this? And we reached out to a number of companies. SSI responded and put it in the way of Nick. So we started doing tests. This is the first one we did earlier this year in March. So we brought the team that are ordering the client for this house to see could we actually use ShipConstructor. And it turned out it could work much better than we even thought. And of course, if you look at like this institutional kitchen, you feel like, what has this to do with the ship? But if I take the same view, this is an 8-story building, and I take away all the walls and floors, it looks like this. 70% of the cost of residential buildings today are installations. And these are pretty much the same stuff you put in a ship. So it's this huge potential. And the inefficiency today in the industry, while this looks kind of impressive for somebody, this model is terribly incomplete. At least half of the stuff is missing. And if we look at, this is the electrical things. It should, could you, I don't know if I'm supposed to. You have PowerPoint? I really don't. We go back. It's an animation of that. Can I? Or should I go back? It's all the electrical part. But you see that it seems like it's all wireless, right? Because they don't model where the cable should go, anything like that. And the 3D models they use for, like, the big circuit box in your apartment is just a box. It doesn't have the bolts. There are no those 25 holes where you need to connect stuff. So you can't do any material takeoff or anything. But even worse, they don't make time plans or plan for how to build it. They have this rude model of the ready building, but there is no work on how exactly would you go about to build it. So what happens is that you on site, while you're actually building it, you solve all these problems where to do the electrical things, and they cut the ventilation, etc. on site. And this is a typical way they do it. And of course, because you do it by hand and systems are more complex today, that's why you have this enormously ineffective and worsening industry. So even if, you say, oh, we ship people, should do better, and we're not the masters, but, compared to this, you're 20 years ahead. And that's why we are interested in trying to use software like ShipConstructor. So it's been really great to have the support of you guys. And Stefan, who is actually using it for a real factory.
Yes, thank you.
Hi, my name is Stefan Wertheimer. I'm here from Sizes in Sweden. We're actually celebrating 1 year today since we entered our new factory in Oskarshamn. And with the introduction of Lars, that's pretty much where our ideas came from, to start building in a more efficient way than residential buildings are built today in most areas. Here is a diagram showing productivity improvement, or actually not only improvement, but if we look at the manufacturing industry, since 1993, we have had almost a tripled efficiency improvement. But if we look at construction, we actually have a minor decrease. We're minus 2%. Very much depending on what Lars just told you here about doing stuff on site, taking decisions on site. Everybody needs to know pretty much everything about their system to do it live. So this, in combination with the cost development of building, we thought there must be something we can do to go along the better path here. So, as you know, there are other factories doing residential buildings. What we are doing, we have started using a fantastic new material, not brand new, but new to many people. It's CLT wood, cross-laminated timber, which is more or less just solid plates of glued together wooden boards. We are also trying to go at this from a manufacturing or a factory point of view rather than a building point of view. So more employment of automation engineers than regular carpenters. We started constructing this. It's a system. It's very flexible, but it's made up by standardized components such as walls, floors, and etc. And we try to minimize the number of parts to make this ready for automation. Today it's very much still manual work inside a factory, but it's all aimed at finalizing a product that's ready for automation. This will lead up to, or already led up to, a very much shorter time to deliver a finished house. We are also today actually having our new guests in our first finished project in Sweden. It's this house you see here that also has 2 sister houses outside of the picture with 32 apartments. Traditionally, it takes somewhere between 4 to 8 months to do the engineering of a house, and it pretty much continues until the house is finished. We aim for something like 4 to 8 weeks instead. And this is where ShipConstructor comes in as a major part of this. So we want to do, after the architect's done, we want to bring it all into a 3D model in ShipConstructor, and the enterprise platform is really what compels me a lot. We have gotten as far as 6 weeks into this, so we're brand new to this. But I'm very eager to see where we can get with this. First, in the manual production sequence, where we can use the enterprise platform to digitalize our drawings and update on the shop floor. And then in the next step, to bring it to something like what we saw with the robots. We won't have welding robots since we're working with wood, but we will have cutting machines, for example, where we can bring data straight down from ShipConstructor and automate something like 40% of this process. Thank you.
Right, so what does that mean in terms of ShipConstructor? And tribute to Lars, who actually saw the similarities in the process. And this is how we go about it. picture of a finished building, which is similar to an ongoing project there. And the way it is approached, because it has to be built in volume units, volume elements, which is what we saw earlier in one of the slides, which is effectively, if you may call it, a box, but it's a complex box because it is a box complete. So when it is delivered to the building site, it has to have everything in it: the pipe, the ventilation, the electrical, the sockets, the kitchen, the bathroom. It has to be completely finished. And obviously all of that has to be assembled. And this is where these similarities appear with the shipbuilding process. And in fact, at first, even I didn't quite see it, but thinking about it and listening to Lars was very inspirational in that respect. So how do we go about doing this? Well, you can see the finished product. This is a Navisworks of a current model. It's one of 4 buildings, but because there are similarities, just like you repeat containers on a ship, we can repeat these volume elements in the building. And what you're looking at here is at cruising speed, literally a couple of days of work. But this is a very, very precious couple of days of work because it creates a huge amount of the information that we've been talking about all along. We have the model, we have the data, what do we do, how do we use it? And this is where the exciting part begins, which is how do we support the process? And the process is to deliver this building finished in 4 to 8 weeks engineering, and then maybe 4 to 8 weeks on the site. You saw the crane in an earlier picture. The units come off the truck, they're shipped by truck, come off the truck and go just like a big Lego assembly set. And I picked up a part just to show the ShipConstructor information. No different than a piece of plate, no different than a pipe, so exactly the same thing as a ship. This was the part that got us thinking very, very hard. And in fact, this is where the interrogation, where Lars's interrogation started. He said, the building industry has been doing it forever, so if they had a good answer, I wouldn't need to go think about it. Nobody would ask me to think about it again. His mission was to think about it. And that rang all sorts of bells, like my previous presentation today and yesterday was, we have all this stuff, we have all this information, let's use it, but let's use it in a good way. Let's change, let's leave the old ways behind and just start thinking from a different direction. Let's think out of the box, they say. And the focal point was Revit, because Revit is one of the Autodesk programs that is used mostly in civil architecture, not engineering really. But there are parts of it which are engineering. In Revit, you run pipes. In Revit, you do insulation. In Revit, you have some sort of electrical models. So why is Revit not going all the way to the production like we do? We have design, we have engineering, and we have production. Not for me. So that took a bunch of investigation, and I took the time to go and talk with Autodesk people more and more, and you have to thank them for having been available because, of course, at first the feeling is, wow, you're going to pull the carpet from under my feet. But in truth, the bottom line and the conclusion of this was that Revit is a fantastic tool to create your initial model, just like we do with Rhino, just like we do with some parts of ShipConstructor, and then we make the renderings, and then we do the hydrostatic analysis. It's fantastic for that. And in fact, it gives a huge amount of extremely useful information from early on, but that's where it stops. Not because you can't do it, but because it is not the right tool to go to the production stages, and then some parts are missing. And what looks like an overlap is in fact a fantastic synergy. Why? Because with Revit, we can start with an early model. You get bills of materials very quickly. You have 3D drawings, models, 2D drawings. You can go to Excel. You can export to Excel to ERP. You can support purchasing, and you can support planning at a relatively macroscopic level. What's missing there is the production detail. But what's very interesting to see is that with ShipConstructor and the SSI platform in general, we also cover all these bases. But so is it really an overlap? No, because we will cover them in a completely, and we do cover them in a completely different way. And the difference is the level of detail. So we're preparing a model for engineering, for production. We're not preparing a model just to extract drawings or, so to speak, just to sell the apartments. And in addition to that, we take over in the part that then goes to the factory. And that is going into necessary detail to get down to the nuts and bolts and to the sockets, to get to the industrialization. This is what we used to call the build strategy. go and support production with everything we've talked about in these 2 days, enterprise platform drawings, work packages we haven't seen yet, and finally go to the PLM process, which is really collecting all of these. When we start looking at it, how do we use these tools together? Because the classic approach would say, I finish using Revit, and when I finish using Revit, I'm going to get building permission, just like we go to the classification society where our steel drawings. Classification today doesn't ask us to evaluate, analyze, and approve systems. Only when it comes to LNG, they're a little bit more attentive, but they say, I'll check how you build it. But nobody is going to impose that you use a certain diameter pipe to run fresh water, black water, and so on. This is all calculation that we do. So that is in the concept phase, really when we are creating the design. It's let's call it early engineering. But already here we get, from Revit, for example, and not only, but from Revit, we get, in the concept phase, we get a lot of information that serves procurement, because we get a macroscopic bill of materials. So a little bit like when you do a weight estimation and you don't consider clashes between steel plates in the ship, you say, well, those clashes are going to be compensated by all the brackets that I have not modeled yet. You go about it the same way. I will have so many square meters of raw plate, raw CLT, the cross-laminated timber. I will have so many square meters of raw carpeting, of raw flooring, etc., which then, of course, we can nest and we can optimize all that, but at least we know where we're going in that respect. So procurement begins at the concept phase. And this is very important because the lead time on such a short schedule is absolutely crucial. Even us in ships with lead times of weeks on projects that sometimes take years, can really have a crucial situation. But we start the industrial process very, very early on. And this is something that I promoted very enthusiastically in our industry for a long time, which is start your industrial process as quickly as possible. And we saw, for example, feeding ShipConstructor with an Express Marine model. We'll hear about Napa Steel. All of those things, if used in the right way, can be incredibly supportive and incredibly productive. We'll talk about more of that tomorrow. So starting the industrial process during the concept phase, obviously you're not going to go crazy and model stuff that you have no clue about. But when you look at all the things that you can do from early on, the list is very, very long, because I can take an initial model and transform it into an industrial model. I can now use all of my inspirational sources from the Revit environment, and not only, not just to drive the early procurement, but also to drive the early industrialization. What are the constraints required by? We do calculations, we go see if the welder can actually fit in the double motto bottom and make that particular weld. We calculate those things, we take care of those things. Same here. If I have something that has to go between the ceiling and the roof, probably easier to put it in before the ceiling goes on, and so on. So there are many activities that can start extremely early, and procurement is already began here. And procurement doesn't mean that you're actually sending out a purchase order for exactly that. Procurement, you're saying that in a panel line, like our panel lines, the CLT panel line, like Marcel was explaining earlier, I am going to book a spot to cut 85 panels, which are going to be more or less of these dimensions, and I have those dimensions from the Revit model, and then I still don't know how many holes I have in the panel, what the details are exactly of each panel's perimeter, but I'm booking because they're booked by length, and the length is time, and the cutting time is what drives the machine. So 4 months, 3 months, 2 months in advance, and these are the lead times that the manufacturers demand, you can already say, I'm going to book you for all of this work. Is going to take you however long it takes you, but now I have the slot. In a sense, it's like purchasing futures in the steel market for the ships. And in practice, this is where it works. You take a 2D plan coming from a Revit model, which is just a section, and we'll see later this is a simplified plan where we have hidden a lot of the drawing over here, and you make a box. Why? Because this box is going to be your volume element. So these are the faces of that cabin that is going to be built in the assembly line. So not in the carpentry shop, but in the assembly line, which is very different. And the convention is very simple, that the outside faces are the outside of the CLT panels. The top face is the underside of the ceiling panel, and the bottom, which we don't see here, the bottom face of this box is the top level of the bottom panel. Why? Because then we extrude to the outside, and we don't have collisions with the walls. And then, of course, the walls will have to be cut to fit according to the scheme that will be decided for that particular volume element. But in the first calculation, you don't really care about 10 centimeters of overlap, because that's not going to change your final supply and your final order significantly anyway. And then, just by using, this is structure, plate elements, they're 25 centimeters thick or 10 centimeters thick. We make the walls, we make the floor platform, and we make the ceiling, which is hidden in this case. You cut the openings, and then you start placing in your equipment parts. The doors, the windows, the furniture, etc., which come either from Rhino or from Revit or from the suppliers or whoever. But right now, I have an exact measure of this panel. The weight and the center of gravity, which are important, because when I put it on the truck, I have to know that this thing weighs 18 tons and not 27 tons. I have to know where the center of gravity is when I pick it up with my forklift, that it doesn't tilt over to one side, etc., etc., etc. Also, the weight is very important, because when you do your structural calculations, the bottom floor holds the whole building up. So there is a structural constraint there, which says not only vertical pressure, but if my vertical mass is going to cause any movement in the structure, yes, it is very strong, but any movement in the structure, I could get a situation where I have torsion that involves a weakness. So very important. And it's like we know with ships, the moment I've done this, I have the exact number, and that number is often a report to the structural engineer, and every day he gets an update with the model so he can see exactly what it is. This is a detail of almost a complete model. You're looking only on the structure here. These are all the insulation layers that are put on the CLT panel. This is the wood, then you have a first insulation layer, then you have a gypsum board, then you have some vertical stiffeners, or supports, and then you have another insulation layer. And the same is for the bottom, on top of which we're going to put underfloor heating, we're going to put electricals and ventilation, and the same goes for the ceiling with the gypsum panel. So these drywall gypsum panels are actually very, very important, because this is what is going to be smoothed before painting. And it's quite a job to manipulate these things, because they're big and heavy and they break, and they make a lot of dirt. So it's very important to put them down on the wood as early as possible. When the wood is on the floor, you can put them down, put them in place, fix them, and then you can plaster them over, and you can finally paint them with difference. This box here is the bathroom. Why? Because the bathroom is a purchased equipment. It's not fabricated in place. Being purchased, it has an outside dimension. It will have to be dressed with the gypsum panels and then painted, of course. And we can see it in this picture, but there is a recess for the door, because the bathroom comes without the door. The door is going to be put in at the assembly line before it goes away. So the door is going to be another equipment, and sometimes you have lead times of 2-3 months before you get your doors and your windows. So it's very important to do this. But to say that, this is all done, by the way, in a single planner group, because it was easier to assemble the UCSs and to just put these parts together. There's still about 300 parts in what you're looking at. And by using UCSs that just are parallel, which we know how to do very well, it's very straightforward to then place your parts. And then we just go to a normal assembly drawing, just like we do with ships. This is not a double bottom unit. It's not a bulkhead. This is an actual cabin. It's one wall of a cabin with a bill of materials with the labels. And what I have done here is I have taken I have moved the wall to a separate planner group, which we can do. So you use a single planner group as long as it is practical, and then particularly if you have several people working on it, you simply transfer your parts to other planner groups, and several people can work on the detailing, if there is detailing to do, of the walls, of the floor, of the ceiling, of the bathroom, of whatever. But the initial model done in a single file by a single person, you're looking at literally many hours, not necessarily many days. So what I did here was, in the assembly drawing, not in the planner group, in the assembly drawing, I simply picked the parts, and I used various, I just explored again because I hadn't done it in a while, explore different ways of picking up the parts. And how did I pick them up? I picked them up with Quick Select. The AutoCAD Quick Select, you can select parts by stock. You can select part by stock in your drawing, and so I just called in for the stock of this mineral wool, these are panels, for this mineral wool, for these wooden battens, for this Other type of mineral wool, and for the gypsum, you select by stock, all the parts are selected, or just say click, move, click, how much in one direction in world coordinates, 750, and there you go. And then instead of doing automatic labeling, because these are obviously all the same materials, I just use the manual labeling from the bill of materials, and when I click on it, this knows that it is part number 1 in the list, if I can read correctly, and so on and so forth, and the tag goes there. So you actually find them. This is 16, this is 20, 22 in the list there, and this is done. So once you have one of these, this is not a fabrication drawing, but this is an explanation drawing for the work team. And then, of course, in parallel with this, we have the layer by layer assembly drawings. So each task is going to be, I received this panel. It already has the gypsum board because that happened at the previous station. So the first team puts these down, but now I know what they are. So just like we do with plate nesting, I nest these. I nest these and I immediately get the quantity of raw panels that I have to purchase, and these are nested out of raw panels, which means I save material, but also I save a lot of time, because instead of picking up a new brand piece every time I have to cut a small piece, I now have a nesting sheet with dimensions on it that shows me from this 600 by 1200, you're going to cut these 3 parts. And then I set up a jig table for cutting, and I save a lot of time. And the value of this approach is in the time, not so much in the materials. These, we're going to do nesting. You know, some of them are the standard purchasing length, some are not. But I can do nesting because each one of these has a name and a label, and I will know exactly how to stick a label on it. And the labels I'm going to preprint because I have all this information in my bill of materials. So I push it out to text, to TSV, to Excel, and just like these labels, which come from a file, all of those labels come from a file, and just staple it to my wood. Same here. Some of these are full size, some of them are not. Some of these are full size and some of them are not. But this is the industrialization of a one-off. All of these volume elements are different, all of them. But if you go about it with this kind of strategy, you're now industrializing a one-off, because you're not industrializing if you made the factory, you're industrializing the process. You're not gearing up to repeat the same thing 100 times. And just like the 9-axis robot, the ones that welds 3D double curvature one-off panels, in this case, what we're going to standardize is the drawings, the documents. They will all be standard. So one day to the next, today a guy is going to assemble this wall, tomorrow he will assemble the floor, the next day perhaps he will do something else. But the drawing appearance and the contents of the drawing is what becomes the company standard. The content comes from the model. And this is the beginning of a great adventure, and I really look forward to do it. That's it. And now we have the coffee break.
You bet.